Hello everyone, Trevor May, VRF and Duct-Free Split Technical Specialist here for another Tech Tips mini-series. On this Tech Tip mini-series, we're going to be focusing on the E3 or F5 error code, which is pertaining to the outdoor fan motor speed being out of control. So the first thing we need to document is make sure that we're reading the code out of the appropriate service manual, whether we're looking at an E3 on our outdoor unit or an F5 on our indoor unit. So that's the difference on why I had these two codes up here, to make sure that we're not only confirming that this is what we have on the outdoor unit and at the indoor unit, that we're actually troubleshooting the correct code. Just like we had on our first tech tip with our E1, of course, you always want to reference your flow chart that comes with the service manual. And again, I'll state on here, this is a great way to get you in the right direction in order for some things to look at to troubleshoot this specific code. However, be very wary when following the flow chart, because as I stated before, you end up replacing multiple boards and mechanical components, and your issue will still be there. It's just essentially a guide through that code to help guide you into specific things to start looking at and check. And of course, if you feel uncomfortable with anything, you can always reach out to call directly to myself, and I can help walk you through troubleshooting specific parts of that system. So things we want to keep an eye out for when we're looking at an E3 or an F5 code on a single and multi-zone system. So some things that we want to check first and foremost are going to be basic stuff. So we're going to want to rotate that fan motor by hand. Of course, you're going to want to power the unit off. You're not going to want to do this while the unit is trying to run. Of course, if you're getting this code, the outdoor fan motor is not going to run anyway, but just as a good safety measure, we always want to make sure that we power that disconnect off. So once we have the power off, we want to go ahead and rotate that fan by hand, make sure nothing's seized up with the motor. And of course, if that fan motor is not spinning freely on there, then you may have found your issue. The second thing that we want to check is we want to confirm that there is nothing blocking the fan motor from spinning. If there's anything caught up in there, some debris, or more importantly, in the heating side of things, if we start having defrosting issues where the coil is not defrosting properly, we're getting excessive ice buildup on there, that can certainly make its way into the path of that condensing fan motor and of course block it, and then you'll end up with an E3 or an F5 code depending on where you're looking at on that system that's pertaining to a fan motor issue because it's not able to spin properly. Another good rule of thumb I always tell guys to look at is if you ever paid attention to the outdoor fan motors on the ductless single zone and the multi-zone systems, when the system goes to start up, first you're going to hear your EEVs go to their pre-pulse position. Essentially, they're just going through their test function. They're going to open fully, and then once the system starts, they're going to pulse back down and close to the position they need to be at, depending on what indoor units are calling and which ones are not. And once that happens, you'll see that the fan motor does this little shimmy and a shake. And a lot of guys ask what that is. So what we're doing is from that main PCB, or if it's from the inverter drive board, depending on the system configuration that you have, that is called a rotational reference. So we're pulsating DC voltage to that fan motor to essentially figure out what is the correct direction to spin that fan motor so it does not run backwards. Okay, so when you see that pulse on there, that shimmy and shake of that fan motor, that is a rotational reference. We're pulsing DC voltage to the individual coils on that fan motor, the outside unit. The outdoor unit figures out what is the correct way to spin that fan motor, and then of course the fan motor will start up and run. Now, of course, if you're getting this code, chances are you might see that happening, and then the fan motor tries to start and then shuts down. Yeah, there could be a multitude of issues. Could be wiring connections, could be a board related issue, could be something that's caught up in the fan motor, or it just could be a faulty fan motor itself. Okay, but we want to make sure that there's of course nothing obvious. So we want to rotate that fan motor by hand, make sure it's not seized up. We want to confirm that there's nothing blocking or in the way of that outdoor fan motor as it's trying to start up and run. Once we've got those simple things out of the way, then we want to start getting into the more advanced side of things with troubleshooting the fan motors. So, of course, it's going to depend on what type of fan motor you have, whether you're dealing with an older AC style motor or the newer DC style motors. So, for motors with 3 wires, U, V, and W, just like we have going to our compressor, you're looking for consistent ohm readings across all 3 wires, just like you would ohm out any normal motor or compressor. You want consistency across them. If you're getting wacky readings on one of the legs, chances are you might have an issue with that coil in the fan motor, and when it goes to start up, and I talked about that pre-pulse or that rotational reference, that could be your issue right there and why you're coding out on this E3 F5 code. Now, if you're dealing with an older style AC fan motor, and they're typically known by the 5 wires that go to the fan motor, you want to make sure that you use the chart in the service manual, checking feedback signal to that main PCB. So if you look on here, you have a breakdown between the W, V, and U wires and the 5-pin wires on there. Okay, now you can see in this case, number 5 or pin 5 on there is your black wire, that's your ground. Okay, so as we're going through, like I said, if you look at the bullet points in the bottom here, there should be 3 there. The first one's going to be if you have the U, V, and W, you want to make sure that you measure the resistance between the U, V, and W wires, and we're looking for consistency. If they're not consistent, or one leg is a higher or lower reading than another, a significant amount, the chances are you probably have a coil that's slowly starting to go bad in the fan motor, and that's the reasoning why you're coding out. Now, if you're dealing with the 5-wire connections on there, you want to first power the unit on. When the unit is in standby, which is when you first power it on, you want to measure the voltage of pin 4 and 5. So we look at 4 being the pink wire, 5 being the black wire, in that feedback signal connector or the Molex pin. Okay, if the value is not 5 volts DC, or excuse me, AC with the AC fan motor, change the main PCB. You're having an issue where you're not getting an output voltage on that pink wire, and of course your black is your ground wire. Okay, another thing you can do to check your feedback signal, and what a feedback signal is essentially telling that main board that the fan motor is running at a certain RPM, because it looks for an RPM feedback. So first you want to rotate the fan by hand. Okay, you want to measure the voltage of pin 1 to 5, 2 to 5, and 3 to 5. Okay, now you'll notice on there 1, 2, and 3, those are your signal feedback connectors. The pink wire is actually what's going to send that voltage to the actual fan motor itself. So 1, 2, and 3 are going to be your feedback connectors. 4 is going to be the actual power going to the motor, and then of course 5 is your ground wire on there. So we're doing 1 through 5, 2 through 5, and 3 through 5 to make sure that we're getting a certain amount of voltage feedback through the signal connector. If any of that voltage is not a positive voltage fluctuation, similar to what we see with the L2 and the S terminals on there when we're checking communication, if any of that is not a positive voltage fluctuation, so you're getting a negative to positive, the fan motor has an issue internally with it, with the signal feedback, and it needs to be replaced. So you can confirm, hey, I actually do have a motor issue, and it is because of this signal feedback. Okay. Now, if you do have a positive voltage fluctuation, then that fan motor is perfectly fine. It's setting a correct feedback signal, and if you're still getting those error codes, you might want to start investigating into that main PCB board that this 5-wire Molex plug is going to be connected to, because there could be an issue with that board receiving the feedback from the fan motor, and it's coding out and giving you a false positive. Okay, and again, those are just some things that we can do to check those motors on there. So depending on whether you have an older AC style motor on there, pins 1 through 5, of course you know what to check now. 1, 2, and 3 are your signal feedback. The 4th pin, your pink wire, is your power going to the motor, and then of course your black wire on there is going to be your ground. Now for your W, V, and U connectors on there, those are pretty straightforward. We're going to treat that like any other compressor that we're ohming out or any other motor that we're ohming out. We're just looking for consistent readings across the W, V, and U terminals. And we know if we have an odd reading on one or more legs, chances are we are having an issue with the coil inside of the motor, and the motor itself would need to be replaced. The next thing that we want to check on there is we want to make sure that all the electrical connections are secure and tight. Situations such as vibrations from unit operation can work them loose, especially on the board, not so much with the Molex plugs, or the classic one, animals getting into the outdoor unit, excuse me, and making a nest in there. And of course, they're looking for material to make the nest. They start chewing through wires, and if they chew through the fan motor wire, when it's not calling on there, they're going to separate one of the legs on there, and it's not going to be able to run. So again, making sure all the electrical connections are secure, shutting the power off, waiting 5 minutes, letting the capacitors discharge for the DC bus, and then going through and checking every signal connection on the board to its individual mechanical component. Now, in this case, we're troubleshooting the fan motor, so we just need to make sure that the Molex plug connection going to it is secure, nothing's broken loose, give the wires a little bit of a wiggle, and then also checking the male to female connectors on the main PCB that are associated with that outdoor fan motor. The next thing you're going to want to verify is that main PCB outputting the correct DC voltage to the fan motor. Okay, on the DC models, you should expect to see about 295 to 350 volts DC for the DC fan motor models. Now, of course, that range on there is totally dependent on what your incoming AC voltage is. The good rule of thumb is whatever AC voltage that you're reading on your main or your bus bar of your outdoor unit, you want to multiply that reading, that AC voltage reading, by 1.414. Okay, so we think of DC voltage as being 1.414 greater than our incoming AC. That should give you an accurate DC output voltage reading. You should always have greater DC voltage than you do AC voltage. If you have a less DC voltage than you do incoming AC voltage, you have an issue with your bridge rectifier. What the bridge rectifier is it converts AC voltage over into DC voltage, which we use in this particular circumstance to power this outdoor fan motor and also our compressor. So if you have an issue with your bridge rectifier, chances are you're going to need to replace the board. Only the larger tonnage multi-zone models have external bridge rectifiers. So something to keep in mind on there, and also a good reading and a good rule of thumb that you can guarantee that you'd want to see out of that fan motor. Now, of course, if you're not getting that, you guys know what to do if you're getting a voltage reading that's less, or you're not seeing a voltage reading that's within that range. Of course, you always want to confirm your incoming AC power first. Okay. Another thing you want to verify on there too, I've seen it happen before, even with surge protectors on there, where you have an issue where an outdoor board has failed. You can either see a physical black mark on it, or the board itself is not lighting up. Of course, if the board's not powered, it's not going to send output power to run any compressor or outdoor fan mode. So again, verifying the correct voltage is being sent out from the board, and also ensuring that the board is actually working and is powered, has LEDs, or has a digital screen, that screen is lit up on it. Okay, again, good rule of thumb with that is if you can verify the board is outputting the correct DC voltage, you know that the board's doing its job. Well, then we need to focus on the wiring harness going to the fan motor and the actual fan motor itself, and that's where we would start owning our fan motor, checking wires, checking electrical connections. So they essentially go hand in hand. It's just rolling things out one by one, just like we do with any normal troubleshooting process. Okay. And then finally, if you have a fan motor that is connected to an inverter drive board. So for those of you that are familiar with the ductless style systems, depending on whether you have a single zone or a multi-zone system, there is a little bit of difference depending on the tonnage that you have. Typically right about 2.5 tons to 3 tons is when we start running into the split configuration. And what I mean by that is typically on a, we'll just use a 12,000, so a 12,000 BTU single zone unit. That model has a single outdoor board, not because it's a single zone, that's just how it's configured. So the inverter drive board, which powers fan motors and the compressor, is actually one with the main PCB. So it's one board, and you can tell that by looking at the board. If you look on the underside of it, you'll see this big, almost looks like aluminum or metal component that's hanging off in the condenser section. That is your heat sink. If you have a heat sink on that board and you only have one board, you have an integral board where the inverter drive and the main PCB are one board. You can also verify that in the service manual by looking at the wiring diagram, because it'll clearly depict whether you have 2 or 1 boards. Now, in this case, if you're looking at a situation or a outdoor unit that has an inverter drive board, and you verify either through myself on the phone if we're troubleshooting, or if you're going through the wiring diagram on there, you want to verify that where your fan motor is connected to. If it is connected to the inverter drive board, the same rules apply. So you're still going to have a U, V, and W that you need to ohm out. You want to verify that you have correct DC voltage coming out from that unit. Again, it depends on what your input is. Okay. But finally, what do we do, or what can we do to check that inverter drive board? Because we know how to check the main board, we need to see DC voltage output. But there's a little bit more to that drive board that we can troubleshoot and confirm if there is an actual issue. So here's what we're going to do. On these boards on the back side, this is what you're going to see here. Now on the left side is the split type, or where we have a main PCB and then a separate inverter drive board with that heatsink on there. And typically your outdoor fan motor and your compressor connections feed directly back to that. On the right side is our single zone unit, where it's all one outdoor board, where it's a main PCB and an inverter drive in one. Okay, since we're focusing specifically on the models that have the split type boards, like you see on the left, we'll focus on that one. So you'll see on here, this is typically how we have an IPM continuity check to make sure that nothing has failed internally between the capacitor buses all the way up to the U, V, and W terminals. Now, in this particular circumstance, I have highlighted the compressor terminals W, V, and U, which is how we check that on. You can also do the same exact process by going on your capacitor buses, which we see here highlighted in red. They'll have a positive and a negative post on them. Now, what you want to do is you want to get out your electrical meter. You want to set it for megohm readings. If you have an auto ranging meter, then it will automatically set itself. Or you have a manual option where you can force it into a specific reading that you're trying to take. What you'll do from there is you're going to take your red meter, so the red lead, and put it on the positive terminal. You're going to take your black lead and you want to put it on the negative terminal on here. So you're just checking continuity between each capacitor bus. Okay, you want to verify that these capacitors are good and that they're allowing DC voltage to not only go to your outdoor fan motor, but to the compressor itself. Okay, once you've confirmed that the capacitors are good, then what you want to do is take that same red lead, put it on the positive post, and then you want to go on your U, V, and W terminal. Now you see there's two separate sets right here. You'll see a fan DC, which indicates you have the DC model fan motor, and you have your U, V, and W for your compressor. So you want to verify that you're taking and measuring the correct area, whether you're dealing with a compressor or you're dealing with an outdoor fan motor. Now in this case, we're dealing with a fan motor. So we're going to take our red lead and put it on the positive terminal, and the black lead on there, we're going to put it on the U terminal. We're going to put it on the V terminal. We're going to put it on the W terminal, all while that red lead stays on this positive terminal. Okay, so we're going positive to U, positive to V, positive to W. Now you'll see on the actual flow chart that you'll see, it says about several megohms on there. Typically, I give a range of about 4 to 8 megohms. Once you start reading above that, it gets a little bit excessive. And then you can confirm there actually might be an issue going on within your drive board, or it's not allowing the correct amount of DC voltage to be outputted either to the W, V, and U terminals for the compressor or to the fan motor itself. Okay, so that's going to be the first one. You're going to take the positive terminal, red lead on the positive, black lead on U, V, and W, verify your readings. You're going to go down to the next capacitor bus, do the same exact thing on that positive terminal. Okay, and then finally, you're going to go to your third capacitor bus on here, the same exact thing. Red lead on positive, black lead, U, V, and W. Okay, we're going to do the same thing with the negative terminal on there. Negative, U, V, and W, negative, U, V, W, negative, U, V, W. There you can confirm that you have the correct megohm reading on there. Not only are your capacitors okay, but the path from the capacitors, which filter out that DC voltage, I shouldn't say filter, but essentially they store and release charge to help keep that power, that sine wave consistent, so we have smooth, clean, consistent power, not only to the compressor, but to the fan motor itself too, because as those of you that have attended other classes that I've done, whether it's a basic install class or an advanced troubleshooting class, you know the name of the game, whether it's ductless or VRF, is smooth, clean, consistent power. These systems do not do well on power spikes or being ran off of non-inverter generators. So that's one of the things that these capacitors help do, in line with the reactor or the inductor, which is essentially a choke, which helps filter that DC voltage and clean it up, take some of the electrical noise out of it. So that's how we're going to check the IPM board on here on a split type application. The same process applies on the single zone, or a single board, I should say, but it's not as straightforward as the split type boards. Now you see on here, there's no markings on here. So what I tell guys to look for is you want to look for the actual indentations of where your capacitor buses are, because they still will have those two posts that stick out of here. Okay, so you want to go between your positive with your red lead, and then you want to find where those connections are on the underside of the board, whether you're dealing with an outdoor fan motor or you're dealing with a compressor. So the same rule applies. You just got to be more mindful at actually looking at the physical layout or the printed circuitry of the board and seeing where those capacitor buses are and where your compressor or your outdoor fan motor hooks up to the board, so you can test on the appropriate terminals. Okay, but if you have the split type board, you want to reference this one on the left. If you have a single board, this is what you want to reference on your right. And this is how we can get through it again and make sure that the board, or this, in this case, the IPM board, actually is working electrically and also working properly. okay. Another really good indicator with this type of board that we see on the left here, there are a green and a red light that will be illuminated when this thing has power. Now it's hard to see on this board, obviously, because it does not have power, but if you follow my cursor right down here, this little square down here, there's a red and a green light. If you can confirm that you have power to this board, which you would check right up here, L and N. Okay, that's AC and power coming in. You take your meter across here and verify that your incoming voltage is appropriate to the board. If you have incoming voltage to this board, you verify, let's just say we took a reading and it was 232 into the board, but these lights aren't lit up on here, a red or a green, chances are your drive board has failed. And that's a really easy way to tell if you have a failed drive board outside of course, checking to make sure your capacitor buses are okay, and then also the path from the capacitor buses either to your compressor or to your outdoor fan motor. So hopefully you guys took something out of that. You have a little bit more confidence troubleshooting the outdoor fan motor and also understanding how that power flows through the main PCB. And if you have a split type board, from the main PCB to the inverter drive to your outdoor fan motor. Of course, if you have any questions, you can always call me at my phone number and direct extension above. If you feel more comfortable, you can always shoot me an email as well with any questions you may have. And if you need to get a hold of a ductless or a VRF product manager, their names, numbers, and direct extensions are listed below. And of course, if for some odd reason I'm not available, the guys in our technical service department with their direct extension there are more than willing to help you with any of your ductless or VRF needs if I can't get directly to you, if I'm out sick, or if I'm just on vacation. Thank you guys for taking time out of your day. Hopefully you gained a little bit more insight on this E3 F5 code for the outdoor fan motor, speed being out of control. And of course, with any questions, like I said, please feel free to give me a call. I look forward to seeing you on the next one.